We know the difference between a dx and a delta x, right? Delta x means a change of x.
Yeah.
A little dx means an infinitesimally small change of x. And if I add up all of the little dx's, I get delta x. And delta x is always equal to x final minus x initial. And if only there were a way that we could tell ourselves, oh, that's not just from any old final to initial, it's from this final to this initial. And in calculus, we have a way of doing that. We call them limits. So let's just say, for instance, we go from 2 meters to 6 meters. This would be from and to. So over here, now that we know our limits, we can say final minus initial equals 4 meters. What this is called right here is a differential. And the integral of any differential gives you the thing. So what we are going to do in this chapter with gravitation, and I'm going to do one with energy here first because it's easier, is we are always going to look for a differential. And once we have defined the differential, we just follow the path and it gets us to the answer. So here's our problem that we're going to do, our example that we're going to do today. We have a bar that's suspended above the ground. It has a length of L, a mass of M, and the end of it is a distance of h above the ground. And we want to find the potential energy due to this bar. Now the problem is, this mass is all broken up into little bitty masses, and all of those little bitty masses have different potential energies. So let's take a look at a piece of them. So if we take this little itty bitty slice right there, and we're going to call that dm. And that dm is at a height we're going to call h. And it also turns out that it's at a length of some L between 0 and L. So we'll just call it, I guess, x. So it's at some distance between 0, this is L equals 0, and that's L equals L. So for that little dm, let's figure out its differential, its amount of potential energy. Well, if big potential energy equals mgh, then its little potential energy for that very, very small bit of mass would be not m, but dm, which I'll put in parentheses just so that we see it easier, times gh. That seems simple enough, doesn't it? But you know what we're going to do is we're going to add them all up, because u is going to equal the addition of all of them. And I'm going to add them up from here to there. So we're actually going to go from 0 to L. So we need to make sure, now here's where things get goofy. If as we're producing this, we're not going this direction, we're going this direction, so everything here has to relate to distance. Well, let's figure out how to do that. This is what we're going to come back to. So let me see, we have an h. We know that h equals, if this is x, right, then that would equal x sine theta.
Yeah.
Do we all agree with that? Yes?
Yeah.
Okay. And likewise, just because we're going to need this later on, would you agree that big H equals L sine theta? That any length, any distance along that bar is the height to that little dm is going to be this length times the sine of theta. Well, oh, that gets closer. So now we have, I'm going to put the dm on that side because it's traditional, and we're very traditional people. So we have g x sine theta times dm. We still got a problem though. This is not mass, is it? It's x. And here's something that you've not seen before, but is a very, very powerful tool, and they're called line densities, etc. The line density, area density, etc. We're going to study those over the next couple of weeks. I'm going to define something known as lambda. Is defined as kilograms per meter, which equals, in this case, the total length, the total mass of the object divided by a distance. which in this case was L. If, like this meter stick, it's a uniform object, it is homogeneous, then a little piece of it has the same density as a big piece of it. Well, I need to get a dm out of it. So if this is true, then it also equals dm over dx. Because a very small slice of it, a very small mass of it divided by its distance will give me the same density because it's uniform. So now I can solve for dm, therefore equals lambda dx. Okay, so now I'm going to plug that in. And I get, there's my limits, right? Final minus initial. And du now equals gx sine theta, and dm is lambda dx. I'm going to point to it. You tell me.
So lambda is a constant?
It's a constant
Okay.
because it's uniform. Now, someone asked me later, what if it was not uniform? Then this is terrible. It may not be terrible, but it's harder. And this, as your first derivation, as your first integration, I'm sure as hell not going to start with something that's not easy. Okay? So that would be a constant. Constant or not constant?
Non-constant.
Not constant. 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 Oh, so this is actually just turned into g sine theta times lambda from 0 to L of x. Oh, so now let's read what we have. We are going to take the antiderivative where x is the only variable. And all we have is x. Oh, I'm not too worried now. So u equals g lambda sine theta. I did that so that we know it's not, those are not part of sine, right? And that's going to give me x squared over 2. And then I'm going to remind myself that we're going from 0 to L. Completing it, we're going to put our constants again. L squared over 2 minus 0. Final, then you put in minus your initial. So, can you still see this down here on the video?
Yeah.
All right, and then I'm going to, actually, let's just put it over here. Can you see this okay? Does it need to move?
Yeah.
Okay. So now we get u equals g lambda sine theta times L squared over 2. Now that doesn't seem like much. But we ain't done. We go back and we say, hey, look what lambda is. Lambda is m over L. And you know, by the way, sine theta equals h over L as well. Let's plug all that in. And so we get g, L, so we get g over 2. Lambda, right here, is m over L. We got an L squared there. Oh, and sine theta is h over L. What do you notice about all them L's? They cancel. So I get my potential energy to this bar equals m g big H over 2, which happens to be as if you took the entire mass, you concentrated at its center of mass, which would be H over 2 from the ground. Now, hold on. Listen, please. Listen. Yes, you could have just gotten that answer from saying the center of mass above the ground. But then you wouldn't be learning the calculus that you need to do things that you don't know. We don't do this kind of practice. In other words, the easiest kind of practice to learn something is to take something you know, do it a different way to practice. In your elbow, that'll be easier to muffle. There you go. So when you're trying to learn something, start with something simple that you know the solution. Practice that, and if you get the known solution, then you know how it works. Okay? Now, the most important part of this, please look, the most important part about this is that when you take the integral of d something, you get that thing. So all we had to do was take a very small piece of that object, which in this case was a dm, define it until we had only one variable that we can add up from one end to the other end. And the rest of it was actually simple. You just haven't done this before. And we're gonna do several of these over the next couple of weeks. Always looking for, instead of a du now, we're gonna be looking for a dg, because we're gonna be finding the gravitational field due to extended objects. And that's good for today.
Okay.